I'd like to take a break from the physics and talk a little bit about a kind of differentiation that you might not have seen before. It's called partial differentiation, and the symbol is this curly d. So that represents the partial derivative of a function f with respect to y. This is only important when you have a function of more than one variable, for example, x and y. And sometimes you'll see the derivatives with some kind of bar or bracket around them with a subscript, and the subscript indicates which variables are kept constant. The basic idea of partial differentiation is that only the variable indicated in the denominator is varied and everything else is kept constant, but sometimes that's made explicit with the bar and subscript notation. In many ways, this is a simpler form of differentiation than what you might be used to. The new thing about partial differentiation compared to what you might be used to is that if, say, x was a function of y, if we took the total derivative of the function f with respect to y, then we'd have to account for not only the variation of the function directly due to its functional dependence on y, but also indirectly due to the fact that x also depended on y. The simpler idea is that of partial differentiation, where we ignore any dependence that x might have on y and simply take the derivative in the normal way, just not being concerned at all about whether or not x is a function of y. So in that sense, partial differentiation is simpler than what you're used to, which is called total differentiation. Now, where this becomes interesting in action physics is that the Lagrangian is a function of position and of velocity. And we're going to be interested in varying the path. So when we vary the path, position as a function of time varies. And of course, that immediately implies that the velocity is going to vary, just by virtue of the fact that the position is varying. So you might think that if we were going to take the derivative of the Lagrangian with respect to x, the position, then we'd have to worry about the potential dependence of the velocity on the position. Well, that's true, but it turns out that all we ever actually need to take are partial derivatives of the Lagrangian with respect to x and not worry about any dependence that the velocity might have on x. And also we'll be taking partial derivatives of the Lagrangian with respect to v. So the bottom line is that partial differentiation, it's really just a simplified version of the differentiation you're quite familiar with. If you do differentiation in the most naive way, then you're doing partial differentiation. If you do it in a more sophisticated way, taking account of functional dependencies in the arguments, then you're doing total differentiation, which is probably the kind of differentiation you have been used to.